one of the founding directors and the Chief Technical Officer of Carbon8 Systems. We were a company started in 2006, so we've been around for a long time, but we were very small for a long time, and we've suddenly, during the pandemic, we've grown from 5 people to more than 35 to 40. So so I've been invited to talk about the role of CCU in the building sector, and it follows on very nicely from the previous talk and the idea of mining. So we'll come back to that in a minute. So I want to talk about the CO2 footprint of construction materials. A very quick focus on the concrete industry, because obviously that's where we can make the most impact in terms of CCU. Talk about carbonation and mineralization as a CCU technology. What products can we make, and how can we generate the value, and what's the sort of capture capacity that we can envisage for carbonation and mineralization. Whoops, too quick. So the carbon footprint of the construction industry. It's something that we're not going to get away from very easily, because we have increased urbanization, and you just look at that picture of New York and you can see the amount of different building materials that are in use. Principally concrete, so hence the emphasis on concrete, but also the huge amount of steel, brick, and then aluminium that goes into our global building materials. It was very difficult to find any data on actually what the carbon impact of the construction industry is. So I've got figures there from 11 to 38%. I think it depends on how you look at it, whether it's just, I think it's 38% of the sort of energy related emissions, but overall the emissions are probably a bit lower than that if you take the whole package. But the cement industry themselves admit to between 7 and 8% of all global carbon dioxide emissions. So you can see we've got different sorts of point sources that are dominating the carbon dioxide emissions. Cement plants are not generally near where there are networks for CCS. They are isolated plants because they're determined by the geology rather than by urbanization. And then there's the classic picture that Al Gore used of the brickworks in India, where you're producing not only particulates that are polluting the Taj Mahal, but you're producing a lot of CO2 and eroding the soil in a totally unsustainable way of producing building materials. So the carbon footprint of concrete, I think most, in about 2018, the MPA published a figure that 1 ton of concrete produced 32 kilograms of CO2. But they were very proud to announce that that was a reduction of about 30% on the 1990 figures. Just for comparison, glass has a footprint of 3 tons of CO2 per ton of glass. I'm not going to talk about how we can do anything about the glass industry. It's a real challenge because it's a thermal process. There's been an awful lot of work on trying to reduce the CO2 in the cement component of the concrete. So if you think of the embodied carbon dioxide in the concrete, it's about 75% of it is due to the cement. And that has reduced by 30% over the last 30 years by the major changes that the cement industry are making. A lot of that is driven by the Global Cement and Concrete Association, and they have a roadmap just recently published, which involves 6 different elements. Replacing the fossil fuels in the kilns. So instead of burning coal and gas, move to alternative fuels, including refuse-derived fuel and indeed hydrogen. There's one plant in the UK that has trialed the use of hydrogen to fire their kiln, unfortunately in conjunction with other fuels. Changing to renewable energy for the other energy requirements of the plant. Deploying carbon capture at scale, well, they're going to have a problem because what are they going to do with the CO2? Because the cement works tend to be dispersed sites. Reducing the amount of clinker in the cement. So About 60% of the CO2 in cement is the direct result of calcination of the limestone. So you have to heat limestone up, and that releases the CO2 to get your cement chemistry right. So if you can reduce the amount of that sort of Portland cement type clinker in the cement, you can lower the overall footprint of the cement. They put the emphasis on recycling more concrete from construction and demolition waste. Well, that's very well, and I can talk about that in a little bit more, how important mineralization is in that area. But in the UK, for example, 95% of concrete demolition waste is already recycled. We can enhance the level of CO2 uptake in concrete, it says, through recarbonation and enhanced carbonation. When I started a long time ago in the carbonation world, if you talked about carbonation of concrete, all the civil engineers all threw up their hands in horror. Oh no, that's terrible. That's a deleterious process in concrete life. Because if you carbonate concrete, the CO2 moves in towards the steel and depacifies the steel. The steel needs an alkaline environment to survive. If you carbonate the concrete, the alkalinity disappears and the steel will corrode and the concrete will fracture. But suddenly the concrete industry all said, oh, well, let's encourage the CO2 into that concrete. But we have to be very careful with that. Anyway, but I can argue that 5 of the 6 elements that the GCCA have proposed are directly or indirectly related to carbonation or mineralization. So what is it? It's a natural process. And I think that's really important to talk about, because it's a very low energy form of CCU. In nature, calcium and magnesium ions, generally dissolved in the ocean, are converted to limestone or dolomite through absorption of the CO2 into calcium carbonate. So fossil plants and sea animals are very efficient at converting that CO2 into calcium carbonate. And that calcium carbonate lasts for millions of years. So I've put up an example. This is the White Cliffs of Dover, Cretaceous. I'm a geologist by training, so I like to put up pictures of rocks. So the Cretaceous, few 100 million years old. So it's been around for an awful long time. And we've used limestone or marble, which is the same thing, extensively as a building material. And there, because I've got an Indian theme, I put the Taj Mahal up. Here's a beautiful example of a marble building, which is quite old. It's been there without too much damage, except for the brickworks down the road who are producing particulates that are changing its color. So there's a very strict regime. You can't have brick making too near the Taj Mahal. So the concrete itself will carbonate naturally through reaction with CO2 in the air. And it's a really simple reaction. CaO plus CO2 gives you calcium carbonate. So that reaction that takes millions of years in the geological column or the geological context can be accelerated if you just increase the amount of CO2 that you've got in the environment, or you manipulate the environment a bit. You put a bit more moisture in, or you change the pressure conditions. And people are doing carbonation at high temperatures and pressures, and in wet carbonation with a lot of water or with only a small amount of water. So there's a variety of different ways of doing carbonation. But basically it's the same reaction as going on in nature. Calcium and magnesium, oxides, silicates, hydroxides can be forced to react with the CO2 to form carbonates. And you can use those carbonates to bind the materials together or produce other sorts of products. So these minerals can be found in natural environments, so particularly basic and ultra basic rocks, so basalts, serpentinites, and danites. You see, I'm a geologist again, I like to throw these rock names out. But also, more importantly, particularly if we're talking about circularity, you can find those minerals in a range of industrial thermal residues. So steel slags, ashes from energy from waste, cement and concrete residues, etc. But most importantly, the reaction is exothermic. That means it gives out energy when you get the conditions right. You don't need to put in a lot of energy. I'm fed up of reading papers which says mineralization is not possible in scale because you need to put so much energy into it. No, you don't. It's an exothermic reaction, so you don't need large amounts of energy. And it's permanent capture, as illustrated by the chalk cliffs of Dover or the Taj Mahal. And you can use both pure CO2 and directly captured CO2 from either flue stacks or from direct air capture plants. You don't need pure CO2. And you can make lots of different products that admittedly tend to be this low value but high volume market. And that's quite an important thing because you're not distorting the market when you're making these products. So if you make aggregate from residues, it's entering a huge market, and you can design your aggregate to fit into a niche market. So you're not causing problems within the general aggregates market. But just listing the different products, we've got supplementary cementitious materials. These are the things that are replacing the clinker in the cement, so lowering the overall carbon footprint of the cement. We can make cements that don't hydrate but carbonate. A lot of work has gone on in making concrete blocks where the strength is derived from carbonation rather than hydration of cement. And then the world that I live in at the moment, which is making aggregate using the calcium carbonate to cold bond manufactured aggregate for a variety of construction applications. So just quickly about supplementary cementitious materials. There's an awful lot of work going on at the moment trying to look at construction and demolition waste, because if you think you knock down a building, it's like having an urban quarry. So you've got a lot of material readily available. Several projects have been using the C&D waste to make SEMs, partly driven by the fact that our other SEMs are diminishing. We use extensively PFA from coal power, coal-powered power stations, and also blast furnace slag have been used in cement for a long time and have important properties in the cement. But if you carbonate the calcium silicates in the cement, you can produce both a calcium carbonate and a silica phase, which provides a limestone filler and what's called a pozzolan, which helps with the cementitious properties of the overall cement. So as I say, there are various European projects, and a lot of the cement industry have got interested in using C&D waste. I've put Carbon Cure in here. Carbon Cure is a very good example of a company that's widely expanding, particularly in the North America, where it's like a supplementary cementitious material in that they add CO2 to fresh concrete as it's poured, which, although they don't use an awful lot of CO2, it enhances the hydration of the cement, speeds it up, so that you can use less cement for the same strength. And they say over the last 4 years of their operation, it looks fairly modest at 160,000 tons. But if you think at least 50% of that is in the last year because of their expansion, I think they have great potential, because every cement truck or concrete truck could have CO2 fitted to it. So carbonatable cements, manufactured from a variety of natural materials, or sometimes thinking about, again, the industrial thermal residues that could be used. So these are producing calcium and magnesium silicates, which don't hydrate, but if you mix them with both water and CO2, they can go hard and cement materials together. Probably the most famous of those is Solidia, again in North America, where they're manufacturing a cement from a wollastonite type silicate. And they're using that cement to make concrete blocks by curing at relatively high temperatures and pressures in a CO2 chamber. Then the whole field of concrete blocks, a lot of companies are using steel slags, again, the calcium, particularly calcium silicates in steel slags. You can form that into a block, cure it at high temperatures and pressures, and make very nice concrete blocks with no Portland type cement in at all. And Orbic's already mentioned, a spin out from Vito, and there's Carbicrete in Canada as well as a number of other companies looking at the use of steel slags. Going on to the mining, we've got, yes, sorry, in mining waste, MCI using mining waste to extract the magnesium and make blocks or boards from magnesium carbonates. And then there's serpentinites where Cambridge carbonates are again manufacturing blocks. So in the aggregates field, again, people using C&D waste because of it being in abundance, and Blue Planet in the USA extracting the natural aggregates and sand from the concrete and demolition waste, and then solubilizing the calcium ions from the cement fines and precipitating calcium carbonate to make nice limestone, what I would call ooliths or rounded aggregates. Similarly, the New Stark in Switzerland are doing that, and they are the first company to earn methodology approval for removal certification in the voluntary market so that they can actually get value out of the CO2 that they're capturing. And they say that they can have concrete with a 10% improvement in the carbon footprint. And of course, I must mention us, Carbon8 Systems. We're treating a whole range of industrial residues. We're using flue gas derived CO2 directly to make an aggregate. Again, tends to mostly go into concrete blocks, but it has some other applications. I'm sorry, I'm overrunning, am I? Okay, that'll be very quick. Just to think about the value and the quantities, the vital bit is underneath the label at the bottom there. If you took all the residues in Europe, you've got about 28 million tons of CO2 that can be captured per year in Europe. That's the amount of residues over 1 million tons globally in these just 5 different thermal processes. So the value of that in terms of market size is 1,200 million pounds. So it's a good commercial enterprise. There are many companies that are already fully commercial, TRL 9, and those companies have had major investments over the past few months and recognized in that voluntary carbon credits market. An important thing, we can permanently capture gigatons of CO2 in a value generating process. So to capture a ton of CO2 in our process, you can make €200 rather than it costing you. Products tend to be low value, high volume, lots of growth, and we must be looking at environmental product declarations and LCAs to prove the carbon credentials of the materials and those things that we need to do as well.